The most important part of regression that takes you beyond what you've done before is regression diagnostics. So you have to look after you've completed your regression to see how effective it is as a model. So there's various things that you can look at within diagnostics. The most important is probably the residuals. So that is the difference between your predicted values and the actual values that you had. So in the top of these particular images, what you've got is a curvature within your set of data. So the residuals are high when they're at low values of x, and they're high at large values of x. They decline towards the middle and become negative. So this is showing that you've got a non-linearity problem. The second plot of the residuals, you can see that there's one point that's particularly far from the rest of them, which is scattered evenly about a horizontal line. That's telling you that you've got an outlier within that particular data set. And the third one, what you've got is a sort of widening of your plot. So the plot of the residuals makes a sort of cone shape. So in this case, what you've got is what's called heteroscedasticity. It means that the variability of your data is increasing as you increase x. There are a couple of other measurements that you can make, to a couple of other derived things that you can calculate in SPSS, which are called leverage and Cook's distance. So leverage tells you how much contribution each of the points makes towards defining that particular line. So if you look at the left hand side, you can see that point 1 is having a very significant effect on the slope of the line. With point 1 included in the dataset, then the fit to the data is the red line. But I hope you can see quite clearly that the blue line is a better fit. So if we remove point 1, we go to the blue line fit for the data. So this you can see in the leverage. So you can see that that particular point, point 1, is altering the slope of the line quite significantly. It's levering it to a different slope to the best possible fit you can get through the data, because it's an outlier and a wrong data point. Other things you can look at is the QQ plots to compare the residuals to see if they're normally distributed. They should be normally distributed, in which case they will fall along the diagonal. If they are skewed in any sort of way, or if they've got outliers, then you will see deviations from those particular points. Now, let's look at some other examples. So here you've got a data set that's got a fit, and you've got a significant outlier at 2.6 probably. So when you look at the residuals, you see a large difference. If you look at the residuals, can either be the native value, or they can be moved to a scale which goes between 0, or which has an average of 0, which is called a standardized residual, or they can be studentized as well, which is another form of standardization of the residuals. So in this case, looking at the residuals, you can see that one is very different to all the others, especially in the standardized residuals. It's a long way away from 0. In Cook's distance, you can see that there's a large distance that corresponds to that particular point, but it doesn't actually affect the leverage. Here you've got curvature, so you see curvature in the residuals. You see the Cook's distance goes up at either end, but again, nothing happens in the leverage because it's the best possible fit that you can get to your set of data. In this case, you've got heteroscedasticity, so the variance increases as you go up to higher values of x. The Cook's distance increases, but the leverage plot is still showing just its usual curve and nothing particularly special. Here you've got an uneven spread of data, so that means that that single point out where x is 3 is making a very big difference to the slope of the line, because you've not sampled your data over a very evenly across x. You can't see anything particular in the residuals, they're both scattered, the Cook's distance is showing that a few points make a big difference to the slope of your line, and you can particularly see this in the leverage. That single point almost completely influences the slope of the line, and particularly you shouldn't have points at the end of your data having such a big effect on your the slope of your line. In this case, you've got a single residual and a single outlier which has such a big influence that it's actually changed the slope of the line from where it should be. So you've got very large residuals, you've got a high Cook's distance for that point, and you've got a high leverage. But to be honest, if you're plotting the data, this won't happen, because you can see clearly that your regression has failed. And even more for this highly ridiculous case where you've got two outliers which completely change the direction of the correlation between the two and completely change the regression model. So the model is a poor fit. You've got bouncing up regression diagnostics for your residuals, your Cook's distances are all over the place, and you've got high leverage for two particular points. This is why plotting your data in a scatter plot is very important before you do any analysis, so you know what you're expecting to see in your regression. Now, as well as single regression on a single variable, you can do it in multiple regression, which has 3 dimensions or 4 dimensions, however many dimensions you want to do. Mathematically and visually, this becomes extremely complicated for us to do. Not many people can think in more than 3 dimensions, but computers can easily solve these kind of problems, and SPSS can easily deal with as many variables as you wish to include in your regression. But there's always the danger of including too many variables in your regression and doing what we call overfitting your data.